9.2, we're now going to be estimating a population mean. So we're going to say, okay, what's the best point estimate for a population mean, and how do we go about constructing confidence intervals for means? It says, our goal in this section is to estimate the value of an unknown population mean. What would be the best point estimate? And this is where it kind of trips up people, and it shouldn't. If you don't know the population mean, what's the next best thing? If you can't ask everyone, you take a sample, right? So not a population mean, but the sample mean. What's the symbol for sample mean? You got it. All right. So in our homework, just like in 9.1, the first parts of these will be, what is the point estimate? And you'll just grab that sample mean from the word problem, and you'll go with that, okay? The rest of this page, guys, is a lot of wordy word stuff, but all it's saying is in 9.1, what we did was we started our confidence interval with the point estimate, and then we added and subtracted the margin of error, and this is how we calculated our margin of error from 9.1. Where did it come from? It was actually the critical value times the sampling distribution's standard deviation, okay? So if we mimic that from 8.1, does this look familiar? That was the standard deviation for 8.1 when you took a sample size. It was sigma over root n. So in theory, so keyword in theory, don't circle or highlight anything yet, we would do this exact same idea. Take your point estimate, x bar, and subtract z off over 2 times your standard deviation and add it. Why we can't do this, and this is something that if I forced you to do everything by hand, it'd make a little bit more sense, but since we've been using our calculator, it doesn't make as much sense. But way back when in chapter 3, when we did the formula for sigma, we had to use mu, your population mean. What are we trying to estimate? Mu, your population mean. So how do you estimate mu if you don't know it using something that needs it? You can't, okay? So it's kind of like a catch-22, and that's all it's saying. It says, how would we estimate the population mean mu using the population standard deviation sigma, which relies on mu, okay, when we have to know mu in that case. So what we are introduced to, this is something that's totally different. This is what I would star or highlight. It's called student t's distribution. I never knew why it was called student t's distribution until I talked to another instructor here. She teaches math for elementary teachers where she has them do a research project on a mathematician. And student t was actually someone's pseudonym. He was an engineer in Germany and didn't want to get caught by his employer back in whatever 1800s or whatever. He didn't want his employer to know he's doing this stuff on the side, and so he just went by student. That's all it is. And so this is what he found was basically you can find a z-score, but instead of using x minus mu over sigma root n, you use x minus mu over s. And so the only difference is you use your sample standard deviation instead of your population, okay? The one new thing that's kind of new you might want to highlight or underline is n minus 1 degrees of freedom. So since we are taking a sample, it depends on your sample size a little bit, and that's what that degrees of freedom gets us to. So go ahead and flip it to the top of page 6, guys. We're going to talk about student t's distribution. It's so similar to your z-score and your normal distribution, so we're going to fill in these blanks pretty quickly. Nothing too exciting about them at all, okay? The number one thing that's different, though, is number 1, it relies on your degree of freedom, which relies on your sample size. And before, your z-chart, it didn't matter what your sample was. You always could use that same z-chart, okay? It is still centered at 0 and symmetric at 0. So when you go to draw the curve, guys, what can go right in the middle? 0, just like your normal distribution. Guess what the total area under the curve still is? 1, okay? Which means the area to either side of 0 is 1/2, okay? So all of that's the same so far. You centered at 0. The total area under the curve is representing probability, so it's still 1. 4 is the asymptote, okay? As t increases without bound, the graph approaches but never equals 0 in either direction. And again, I think that's super cool that it's an infinite graph, but it still equals exactly 1. All right, so this is kind of, again, the key difference, so we'll start number 5. Why is it a little bit differently shaped is because we're using S to estimate sigma, Okay, so we're using our sample standard deviation to estimate our population standard deviation, which gives us a little bit a different shape. And last but not least, it's important to know that no matter what, guys, the law of large numbers states no matter what the shape of your distribution, as n gets bigger and bigger and bigger, you approach the standard normal curve. So S will look closer to sigma and so forth, and so the t distribution actually looks more and more like your z distribution, okay? What's different though is we have this whole new chart. So if you can, label this 9.2 and 10.3. 9.2 and 10.3. So what we're going to do with this chart is we need to learn how to read it. It's a little bit different, okay? Why? Because we never had degrees of freedom before, but let's remind ourselves that degrees of freedom are n minus 1. Let's remind ourselves that we find degrees of freedom by taking our sample size minus 1. This chart's actually easier to read because, notice up here, this is the area in the right tail, so keyword right tail. And so all of these t-scores, these are actually the t-scores in here. I'm going to write that off to the side. These are actually the t-scores. So turn it sideways. These are all the t-scores, where on your z chart, those were all the areas, right? So these are all the t-scores. All right. Oh, did I get you the wrong one, Jake? I got you. Somebody else have a wrong one? Sorry. I used something else that was golden shaped. Yeah. Did you get 2? Yeah. Okay. Thank you. No, you're fine. I gave you a formula sheet. Everybody get the t distribution with the area in the right tail. Okay. So those are all your t-scores. But what's nice is when we have to do this reverse formula, guys, all of our areas are right up here. So you know how we're saying, okay, the area in the tail to the right is 0.01? Well, you can just go to 0.01 and then scroll down to your degrees of freedom. What I want you to notice is 1 through 40, we have something, but around 40, we jump by tens, and then we go to 100 and 1,000, and then basically after that, it's your z-score. So what you're going to notice is some key ones, 1.645, 1.96, 2.576, kind of like that 2.575. So you actually can kind of use this a little bit for 9.1 if you wanted to. All right, so let's look at what's going on here. On this first example, it's just asking, can we use this chart? So it says, find the t-value such the area to the right is 0.025 with your degrees of freedom of 14. So our degrees of freedom are 14. The area is 0.025. So it gave us everything we needed. It flat out told us the degrees of freedom, so we don't need to do n minus 1. It told us the area to the right, so we don't need to do area to the left or anything. So what we can do, guys, is on this chart, we're going to go down to the row 14 and over to 0.025? What do you guys get? 2.145, okay? So your t value would be 2.145. Does everybody see where that came from? Bless you. But in real life, they're not going to be that nice where they just hand it to you on a platter. They're going to make you do it because we're finding a confidence interval, okay? So we're going to have to figure out our degrees of freedom by taking our sample size minus 1. And we're going to have to figure out the area to the right by doing, okay, 90% means 10%, blah, 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 okay? So let's figure out our degrees of freedom first. That's n minus 1, but we have a t-value if you want to make 90% confidence with a sample size of 25. So what is this? That's our n, right? So what will our degrees of freedom be? 24. Is everyone okay with that? So that tells us what row. Notice how that was different than the one right above. The one right above said 14 degrees of freedom. DF given to you, right? This one just said you had a sample size of 25. So that means they gave you the n in degrees of freedom. You have to subtract 1. All right, how do we find what column to go to? Well, 90% confidence leaves how much for our tails? 10%, which means how much for each tail? 0.05. So that's the column we're going to go to. But what's nice is instead of that reverse lookup, you can just scroll over to the 0.05 column, and it's there for you. What do you guys get when you do that? So you go down to row 24 and scroll over to column 0.05. Yeah, 1.711. And every year I say I'm going to do this, and every year I forget. What if I wanted to know the t value that had an area to the left that was 0.05 with 24? It would just be negative 1.711. Remember, it's symmetric, right? So if the area to the right is 0.05 and the area to the left is just negative 1.711. So keep that in mind, because I think on your homework you have one to the right, one to the left, and the one where it's like the confidence interval. Confidence intervals, you always just leave them positive. But area to the right will always be positive t-scores. Area to the left are your mean, so they're all negative t-scores. So kind of keep that in mind. So area to left are negative t. And we might even write it on our chart. So this is right. So areas to left are just negative. So look it up like normal, find your t-score like normal, and just make it a negative answer there. Alrighty. I want to do one just so people can get homework done if they want, and then we'll leave page 7 for Wednesday. But what you'll find, guys, is that the formula is identical. You start with your point estimate, you add or subtract your t-value times your standard deviation, okay? So again, I'm going to show you how to do this by hand, and then we'll do it with our calculator. It says a simple random sample of 16 restaurants is chosen, and the temperature of coffee is measured. So 16 is what? It's the random sample of 16 restaurants. That's our n, right? The sample mean is 162. So what is that? That is x bar, sample mean. And the sample standard deviation is 10 degrees Fahrenheit. What's that? S. Find the 90% confidence interval for the mean temperature of restaurant coffee if the distribution is approximately normal. Interpret your result. So how do you know which formula you're going to use? Notice it's not talking about proportions or percentages at all. It add the word mean in there. So we're going to use this formula. So our lower bound is just going to be x bar minus t alpha over 2 times, I put s over root n in parentheses. You don't have to, but I do. All right. And again, we can label x bar, s, and n because we already labeled them everywhere in our formula or our problem. We just haven't calculated t alpha over 2 yet. So what was our average temperature? 162 degrees minus, leave a blank for our critical value. And then our S was 10 degrees Fahrenheit over the square root of our sample size, which was 16. Does everybody see why things are going where they're going? So remember, your sample means always x bar. That's always what you start with. That's point estimate. And then you're going to calculate the margin of error. Again, I'm going to do a little arrow like our little footnote. How are we going to come up with him? Well, 1 minus 90 equals 10%, right? 1 minus 90 equals 10% in our tails, or how much in each tail? 0.05. So that's our area, right? But how do we know what row to go to? That's our degrees of freedom. Degrees of freedom are n minus 1, which in this case, our degrees of freedom will be what? 16 minus 1, or 15. So that's our row. So I'm just kind of labeling everything so you kind of know where it comes from. Little thought bubble, okay? So your critical value, you need to know what row you're going to, and that's your degrees of freedom. Your sample size minus 1, so that was 15. We're going to go down to row 15. And then what column is always your area and the tail? Well, if we're 90% confident, that means there's 10% chance that we're wrong, so that's the outside, or 5% chance in one tail. So if you guys go to row 15, or excuse me, yeah, row 15 in column 05, what do you guys get for your critical value? 1.75. Perfect, 1.753. Are there any questions on where those numbers came from? And again, we can do this on our calculator, but I am going to have a problem on the test that says, if we're doing a t-test, what would the t value be? So you do need to know how to figure it out. Let 162 hang out with you guys as you calculate that, okay? So put it in your calculator exactly how you see it. 1.753 times 10 over root 16. Let's round to 1 decimal place. What do you get for your margin of error there? 4.4. You got it. So what does that mean? It means the average coffee temperature is 162 degrees Fahrenheit, give or take 4.4 degrees, okay? So your lower bound's the take. So 162 minus 4.4 is 157.6 degrees Fahrenheit. And then your upper bound is the give. 162 plus the 4.4. So that gives us an upper bound of 166.4 degrees Fahrenheit. Okay, so what does that mean? Instead of what we would have done before, said, I don't know, I asked 16 restaurants and their average was 162 degrees. We can now say, no, I am 90% sure. 9 out of 10 times you will have a temperature between 157.6 and 166.4. We're going to always have to interpret these. Guess what? The sentence is exactly the same, but now we're estimating the true population mean. The true population mean. So we are 90% confident. We are 90% confident the true population mean temperature of all U.S. restaurants, coffee, but I'm not going to be that wordy. So we are 90% confident the true population mean is in the interval. And usually when I do the interval notation, I don't worry about the unit, but you're really supposed to. I put the upper one first for some reason. How do you do it on your calculator? You go to stat, scroll over to test, and you just go to a t interval. Move it over here. So I'm going to go to stat. I got to turn my calculator on. Stat, test, go down to a t interval, right below z interval. So we want a t interval. You hit enter. Okay, data means you have raw data that's in a list, but we don't. We have statistics. So what was our average? 162. What was our standard deviation? 10. How many people did we ask? 16 restaurants. What was our confidence level? 90. And you hit calculate, rounded to 1 decimal. 157.6 to 166.4. Okay, so guys, we'll finish, sorry again to kind of shove it down your throat, but we'll finish 9.2 on